kind of see that it's not 0 here. You can see that. And then as you go to right, we get this. And then how about if you now, get the point? How about, let's say, can you put an x comma y? No. A comma b. Let me see. You know what? How about this? Let me call this guy f of x. And then what I'm going to do is I'm going to call this guy a comma f of a. Let's do this. And then how about the sliding scale? How about if you let this a be, let's say, how about 80? Oh, there you go. Label. Oh, there you go. You know what? Now I mark the point there. This is the point. So this is a long graph here. Now you can see it's 80. So this is the graph here, same graph. And then now at 80, when x equals 80, we find the point 80 comma 0.542. So at that point, the y value is 0.542. Looks like it is not 0. How about if I now change that to 800? What is that now? Now we get the point 800 comma 0.504. Okay. So now you get the hint. Oh, so maybe the answer might be half. Is the answer going to be 0.5 or is it going to be 0.50501 or something? We don't know. And so you can get the hint. So if I magnify this further, how about let's make it? How about if I make it now 2,000? That's what my scale is right now. So 2,000. Okay, let's see what. Oh, now it's 2,000 comma 0.502. Okay, so is it going to 0? No, we don't know. We don't know that. But now you can increase that here. Okay, then now do this. Now how about if you now increase that to 5,000 now? When x equals 5,000, that's what happens then. Oh, at 5,000 now 5,000 comma 0.501. Okay, all right. Okay, so now we can kind of estimate. Maybe the answer is half. So do you see that? So if you use a calculator like this, you know what, you can kind of estimate. But can you be sure that the answer is 0.501 or 0.5? That we're not sure. Who knows? Maybe the answer is 0. Maybe the final limit as the f goes to infinity, maybe the answer is 0.501. That we're not sure. How about if you now put this, maybe put in, let's say 12,000. 12,000? Oh, now we see that 12,000 comma 0.5. So I think that 0.5 is still an estimate. But we can kind of see that the answer is 0.5 here. If you go back, and the scale is even further. And now how about if I make this to 4,000, 40,000? Okay, or looks like it's now 0.5. There we go. So again, this is, so therefore a calculator has a place. It has its uses. So obviously looks like now it's a strong indicator that the answer will probably be 0.4, the limit. Because even if you move to right here, see, no matter how far you go here, you're not sure. But you know what? Should you try one more? How about if you now try, let's say, 180,000? Oh, 180,000 now? See, 180, not 18,000, but 180,000. The y code is 0.5. Okay. So now, you know what? We can kind of see that the limit is probably 0.5. But again, it's not conclusive though. Now, on the test, if you give me this kind of argument, am I going to accept this? And the answer is what? No, I'm not going to accept that. So on the test, you have to show it mathematically. So if you show it mathematically like the way I show, then now it's absolutely clear that it is 0.5. Okay? So in this case, this is not absolutely clear. Maybe the answer is 0.499. Who knows? We don't know. And how far do you have to go here? No matter how far you go, you can never conclude the limit. But it looks like it is clear. See how, no matter how far we go here, and we'll look at this here. We go like this. Let's see the graph here. Now I'm really scaling big. Now it's really big. But it's not clear. So now we can plug in 2 million if you want to. Let's see what happens if you plug in 2 million. 2 million? Oh, now it says 2 million, then comma 0.5. So it is almost conclusive. However, again, this kind of argument is not going to be accepted. Is that clear? Because mathematically, we don't know. We really don't know. I mean, the graph is like this, up to 2 million, but what happens at 10 million? Are you sure that at 10 million, the graph is not going to spike up? That we don't know. Mathematically, we cannot conclude. Logically, we cannot make that conclusion. Again, when the x is at 10 million or 1 billion, who knows? Maybe the graph will spike up, but we don't know. We don't know that. Yeah, in this case, I don't think it's going to do that, but we cannot guarantee. Okay, is that clear? Any questions on this calculator? It's just kind of fun. It is definitely a good idea to play with this graphing calculator or even a regular calculator. But again, a graphing calculator or any kind of calculator will not, the result of a graphing calculator will not be acceptable. Why? Because from a mathematical, logical standpoint of view, it's not guaranteed. You cannot really make a conclusion. See? Cannot make a conclusion. No matter how far you go, you cannot really nail it down and make a final conclusion. That is logically impossible. Is that clear? So therefore, mathematically will not be acceptable. Remember, when it comes to limits, or as many other subjects in math, we have to be better than the calculator. Is that clear? If you just use a calculator, you cannot be better. Again, we have to be better than the calculator. Okay, any questions here? Any questions on any of these limits? So what I'm going to do is I'm going to now erase this. Okay.
I actually plugged the equation f of x equals rad x squared plus x plus 7, and it didn't actually display the same type of line as the Desmos one on your screen.
Which one?
The first one, the very first equation. It displays a parabola for some reason.
What equation? What function are you talking about?
F of x equals square root of x squared plus x plus 7.
Square root of x squared plus x plus 7? You mean if I take out the how about this?
Never mind, I found the problem.
You mean fx is this right here without the minus x? Are you talking about this guy?
No, I fixed the problem.
Okay, sure. Okay, so no more questions? Oh, this must, you know what? I have two F's here. That's why it's a question mark. I have to call that G now. The now it's going to go back. So G, yeah. If you have this right here, how does the graph of G of x look like? The graph of G of x kind of looks like this. So this is how the graph of G of x looks like. Doesn't that kind of look like an absolute value of x? It's kind of weird. Interesting, right? If you magnify this part right here, let's see how the graph is going to be near the origin. Let's see, how will the graph look like near the origin? Oops. What is this? Oh, now we see something going on here. Oh, it's kind of lifted up. This doesn't pass the origin here. Sometimes when you magnify, we get to see more things. It's this. Oh, it kind of looks like a parabola. From far away, it kind of did look like y was absolute value of x, but near the origin, it looked like this. Okay, so what is this? Oh, now it's coming interesting. Now the bottom is not even at x equals 0 here, so the bottom is like this. See? Okay, so that's kind of interesting. Anyway, you know what? All these other interesting stuff, we might be able to study some more on this later on in this course. Otherwise, you'll also, you'll continue studying when you go to Calc 2. Okay, some stuff will be covering Calc 1. Other stuff you'll be studying in Calc 2. That is as far as the graphs go. Okay, so what I'm going to do is I think this is the, I think we have done enough decimals now. So let me now go back to our files. Our files is 7.15b. I think we have done enough here. So what I would like to do is now, let's move on. So let me share. Share, we are sharing. Now 7.15 is finally over. Let's now move on to section 0716. So file 0716A. Okay, like this. Okay, now 1.68. Now let's get into limit loss, the loss of the limits. And if both the limit of f of x and limit of g of x exist, then you can split this. So these are what we call what I call the limit loss. Okay, so now let me make some comments about the limit laws here. So the question is, when you have limit of a sum, can you write that as the sum of the two limits? And then number 2. Oh, you know what? There should be some space here. There's no space. Now, question on law number 2 is the limit of the product. Is that the same as the product of the limits? Is that true? And then the third one, the quotient. If you have a limit of a quotient, is that equal to the quotient of the limits? In other words, in all three cases, can you split the limits? And then I didn't do any subtraction here, but subtraction here is the same thing as plus here. So when you have a difference of limits, can you take the difference of the limits? And the answer is this. Kind of yes, but the answer is this guy right here. Only if these limits exist. Only if this limit right here exists. So let me mark this in bold print because this is very important. If both of these limits exist, so if they don't exist, we cannot apply the rule. You're right. If these limits do not, if these limits exist, then you can apply. But now here is the question: what does it mean by saying that this limit exists? What does it exactly mean? The limit of f of x. And then I'm going to put x here with some kind of x here, x approaching something. Doesn't matter what kind of, what x is approaching. X could approach infinity or 0 plus or 3 or 3 minus 3 plus or any kind of limit. If this limit exists, what does it exactly mean? This limit exists. What does it mean by this? What does it mean by this limit exists? Let me tell you what this means. Let me tell you, explain to what this means. So this right here, let me put this in parentheses here. This limit right here exists. What does it mean? It means that the limit is actually a real number. Limit of f of x is a real number. Is a real number. Let me just put this. Belongs to the set of real numbers. That's what it means. So when you say that the limit exists, the terminology is this. This means that the limit is actually a real number. How about infinity minus infinity? Well, this is the tricky part here. When the limit is here, let me now say this here. If the limit is a infinity, limit f limit of lim f is infinity is equal to what? Is equal to infinity. Lim equal to infinity or minus infinity. We say that the limit does not exist. Does not exist. So here, class, here we now get into a term which is a little bit confusing. So when the limit is infinity or minus infinity, we do not say that the limit exists. We say that the limit does not exist. So we say that the limit exists only if the limit is actually a real number. If like 5 or 10, it could be 0. But if the limit is infinity, we say that the limit does not exist. So this is a bit confusing here. However, on actual problems, the question is, can you split the limit? You can only split if the result is not an indeterminate form. So let me explain to you what that is. It's a bit confusing, so I'm going to save this here. I'm going to save it here, and I'm clear this. So now, for example, let's look at this right here. So let's look at this example 1. If you look at this example 1 here, can you split the limits here? The question is, can you split the limits? In other words, can you write like this? Like this, and then write the split the limit here. So this is now the limit of, you know what, let me write this in small print, thick, lim, and then x squared, and then plus what? Plus lim 3x. And then what? Minus 7. 7, you don't need to put the limit, and then the x approaching 2, and after x approaching 3, and x approaching 2. And then what is the denominator? The denominator is now 4x, and then minus 5. And then here we can put the limit. X approaching what? 2. And of course, we are calculating this limit here, and then this 5 is separate. Yeah, 5 doesn't need a limit because there's no x. So this, and then that, and then 7 right there. So how about this? This here, what is that equal to? That will be 2 squared, which is 4, and then plus 3 times is 6, and then minus 7, and then that will be 4x, which is 8, and then minus 5. So when you do that, what does that become? That becomes what? 10. That's 3, and then 3, and then this becomes 4 equal to 1. The question is, when you split the limits, the question is, this is always the question. When you split the limits, can you split this? The big question we have is this. Can we split the limits? The question is, can we split the limits? Split the limits. Can you split the limits? Can you split the limit, the original limit, into smaller limits like this? Whether that be sum or difference or product or quotient, doesn't matter. Can you split that? Now, in example 1, can you split the limit? Yes, we can, because the result comes up in 1. We get a nice number. We don't get any trouble. We do not get, if not, this is now the basic of this. After you split the limit, after you split the limit, if you get any of the indeterminate forms, indeterminate forms, then split is invalid. Invalid must go back. Then what? Then infinity cannot split. I'm going to explain this rule more clearly. But now in this case, in example 1, so by the way, the question is, do we have to write all of these things here? All of this, are you required to write all this step right here? Can you just go from here to here directly? Am I going to accept that? Yeah, I will accept that. Will accept. Accept? Yes, I will. But do you know why I will accept that? Because in this case, this one and this one accept because what? Because of not indeterminate. Oops, I have no space here. Because not indeterminate. Okay, so now when you plug that in, when you plug x plus 2 into this expression right here, then what do you get? You get this. Is that good? Now this one is very good. It's not one of those 0 minus 0 and all that. So this is very good. So therefore, acceptable. Okay. Game is over. You plug it in, and that's it. It's 1. The final answer is 1. That's it. It's easy. Now let's do example 2. Example 2, limit of x squared minus 4 over x minus 2. So now this one is, what is that? That's a 0 over 0, 4. Now the question is this. Can you split this? This here? Now split?
I don't think so.
Yeah, this one you cannot split. Because if you split this is now quotient. Now what happens if you split this limit here? Limit here, and the limit here. The question is, can you split this limit? And then now I'm going to show you x approaching 2, and then x approaching 2 here. And then now this kind of limit, of course, you have seen it before, something very similar. And then what we see is x squared minus 4, and then over x minus 2. So we might consider splitting this here, but in this case, if you do that, then what happens here? We do get 0 over 0 form. We do get 0 over 0. Therefore, in this case, what can you conclude? Split is not valid. Split is not valid. In other words, cannot split. Must go back. So whenever you get into one of those forms which we studied, one of those indeterminate forms, or anything of that sort, then we have to go back. It does not work. Okay, so in this case, what do you do then? In this case, you don't split the limit. You just have to manipulate this guy until the limit becomes a non-indeterminate form. So in this case, you back to the numerator, x squared minus 4, and all that, and then finally what you get is you get this limit, and then you get what? You get x plus 2. And then at that point, you don't get an indeterminate anymore, and then x plus 2, and then x is approaching 2. Ultimately, you get that, and then what? And then the answer, of course, comes out to be 4. 2 plus 2, which is the answer, is now 4. Ultimately, 4 will be the answer. But what I'm saying is the split does not work here. So now let's look at example 3. Clear all this. Now let me reinforce this idea. So now let's look at example 3. Example 3, correct or incorrect? Okay, so let's say example 3, what do we have here? Example 3, we have this. We have this right here. Okay, so let me use red. Example 3, part A is this guy. Limit of 1 over x as x approaching infinity. So this one, obviously, we know that it's infinity. And infinity is the answer for that one. And of course, even though we said that the limit does not exist, the answer is actually infinity. By the way, in this class, if the limit of f of x equals infinity, then in this case infinity, then write infinity. Then write infinity rather than what? Rather than does not exist. So once again, if the limit comes up infinity or minus infinity, then write infinity or write minus infinity. Don't say does not exist, because infinity is the better answer. Okay? Infinity is the more specific answer, even though the limit does not exist is correct. In some books they actually write it that way, but infinity is the more specific answer, so I prefer infinity. And if it's infinity, I know that the limit does not exist. I know that because I know the language. But if it's infinity, then just say it's infinity. So in this case, for example, if you say this here, or let's say this, how about this? The limit, let's say, how about this here? Let's say we have a limit here. Let's say we have a limit here, and then let's say we have a limit of 1 over x. And this x is heading to x is heading to 0 plus. Sorry, x is heading to 0 plus. X is heading to 0 plus. X is heading to 0 plus. Then what is the answer? The answer is plus infinity. Now, if you say that the limit here, and then x approaching 0 plus here, and then 0 plus. So you might say this is what? This is does not exist. The limit does not exist. Does not exist. So which of this is correct? The limit does not exist, and the infinity. Which one is correct? They're both correct. Both correct. But which one do I prefer? I prefer this one. It's infinity. If infinity is a more specific kind, if a specific case, then does not exist. If you say it does not exist, I have no idea whether this is referring to infinity, or this is minus infinity, or it's not, or it's oscillation. There are all kinds of cases of does not exist. So does not exist is a more general term. If it's infinity or minus infinity, write that infinity or minus infinity, and then I will accept that. Is that clear? But the language is a little bit subtle here. Okay, one has to be a little bit more careful. So now, be this infinity, but now 1 over x right here is equal to x times 1 over x squared. And then, oh yeah, that one, up to that point is not a problem. Now the question is, can you split this? It's now, this is a question mark right here. Can you say that the limit is that right there? Can you split?
No.
No, not exactly. Because when you split this, this now becomes 0 times, and then what? Times? This becomes infinity. Oh. This is, oh no. This is what? Oh no. Oh no. Cannot split. Cannot split. This case. Is that clear? So now if you look at part B, can you split that? No, you cannot split that either. That's infinity times that. You cannot split that. Now let's look at example 3. Example 3, part B, the last one. Let's look at this guy. Example 3, 3 times the limit of 3x squared where x is heading to 0 plus. Okay, now can you split that? Can you write that 3x squared as 3 times x squared? Okay, that's not a problem. And now the question is, can you split the limits now? Now, this part right here will be a question mark. Can you split this equal sign? Can you split that as limit of 3 times limit of x squared? Both as x equals 0. Can you do that? Can you split?
Yes.
Yes. Now, if you do that here, let's see what happens. Well, that one will be 3, and it times infinity. This one is what? Oh, yes. Oh, yes. This is oh, yes. Oh, yes. 3 times infinity, not a problem. Because what is 3 times infinity? You know what that is. That will be infinity. So not a problem. You can split that. Now, what happens if you have, let's say, example 4? What is this guy? Can you write that as the limit of x cubed? What is the limit of x cubed? And then what? Minus 100. Of course, minus 100, there's no x there, so you can just write that as 100 like this. And so we can do that, limit of this guy, and then limit of 100. But 100 has no x, so there's no use of putting the limit there. And so we now let this x approach infinity. So now the question is split the limit as well? Yeah, that is also split. Except 100, we don't need the limit here. So in this case, if you want, I can actually put the limit in yellow marker here, lim. All of you like my yellow marker, don't you? Put a lim there. Oh yeah, now you cannot see, it's so narrow. But lim as x approaching infinity. Again, I can write that in yellow. But we don't need it because this is 100. So that limit of x approaching 100, we don't need it because there is no x there. So the question is, can you split this? Can we split? What do you think?
Yes.
Yes. This one, if you, let's say, now if you see what's going on here, this guy is infinity, and then minus 100. Or infinity minus 100? Yeah, that's good. Very good. This one, we like it. What is the answer? That's still infinity. Not a problem. So infinity minus 100, you know what? Now note that here we have infinity. Now, when we now go back to the top of the page, it says we can split only when the limit exists. But in this case, the limit actually does not exist. The limit does not exist. But can you split? Yes, you can. So here, the rule is very subtle here. The limit does not exist, but you can still split. Because infinity is a nice case of the case where the limit does not exist. Anyway, the rules are a little bit more complicated to explain here. But when you split, if you get one of these indeterminate forms, then you cannot split. You have to go back. If you don't get that, if you just get a nice number, one conclusive symbol or number, then that's it. Split is going to be okay. So infinity here, in this case, what happens? The split is valid. Split, the limit split is valid. So the limit split, so the limit, let me call this the limit split. Limit split is valid. Means okay, you can do that. Now let's look at example 5. Can you split this limit? So this is now the limit, and x cubed, and then minus the limit of x squared. 100 times, and then we can actually split the limit as well, and 100 can actually be split as well. limit and then 100 and then x squared, like this, and then like this here, and then it's this limit right here, and that limit right there, and the 100 can also be split as well, so 100 approaches infinity here, infinity here. Can you split this limit? What do you think? This guy's now infinity, and then minus 100 times infinity, that will be infinity. Good or bad? Can you split this limit?
Bad.
Limit split is not valid. Cannot split in this case. Because the reason why is this. When you split this and write this as infinity and minus infinity, then now we don't know which infinity is bigger. See, if I just ask you what is this infinity minus infinity, then you cannot really answer this question. If I ask you what is this infinity minus infinity, if I ask you this, then we have really no idea because we don't know what kind of infinity we're talking about. If the infinity is not specified, then this will be considered undefined. If we don't know where the source of this infinity is coming from, we don't know where this infinity is coming from, then what? This will be considered undefined. Then there's nothing we can do. So we need to know where these infinities are coming from. And so in this case, we do know it's actually coming from here. Okay, so in this case, split is not valid, cannot split. So when you split this, that will be now wrong. So if I give a problem like this, and then you give me this right here, then how many points off? How many points off? And that will be what? Infinite points off. All right? Is that clear? If you split that limit on example 5, then how many points off? Infinitely many infinite points off. All right, is that clear? So in this case, what do you do? So in this case, what is the correct answer? If I give you a problem like this, so what you do is you what? You write this in what? Write this as a product. So or cube. So how about if you factor x cubed? Factor x cubed here, then that will be what? 1 minus 100x. So right now we are not splitting. No split here. And then x is what? X is approaching infinity. And then now, can you split this and evaluate now? Yeah. When you split this and evaluate now, what you get is you get infinity and then times what? Times 1 minus 0. Oh, is that a yes? Yeah, that's a yes. So what is that? That will be infinity. Again, the rule is this. If you start with an indeterminate form, you have to do your best to convert that indeterminate form into a non-indeterminate form. Or we might say it's a determinate form, but that term, unfortunately, we don't use. I use it, but we don't use the term determinate form. So we'll have to say not an indeterminate form. So if you have an indeterminate form, you must convert that to a non-indeterminate form, like this here. This guy is now a non-indeterminate form. And once you convert that into non-indeterminate form, then you can split this and you can write it down and the game is over. So you must convert this into a non-indeterminate form. So when you have a problem like this here, you cannot say this is equal to infinity minus infinity, but you say that this is big and this one is small, and then big and small here, and so they're small, and so this is equal to infinity. No, that does not work here. That kind of argument is not going to work. So if I give you any kind of limit problem, what do I need to see? I need to see the non-indeterminate form. So for this one right here, if I give a problem like this, I need to see this guy. Or of course, the other option is to factor the x squared. If you factor x squared and then you get x minus 100 like this, that's okay too. But if you write this form, so what is this going to be? That will be what? That will be infinity times infinity form, and that's okay too. Infinity times infinity is infinity. So we have a limit here, the limit as x approaching infinity. So x approaching infinity. So if it's infinity minus infinity form, that's okay at times infinity, and that will be infinity. That's okay too. This is okay too. Everybody get that? Easy? Too easy or not too easy?
I can tell we'll get better at it with practice.
Okay, but anyway, the rule is this. When you have an indeterminate form, you have to convert that argument until it becomes a non-indeterminate form. And then on the test, I need to see that non-indeterminate form. If I do not see that non-hidden form, then don't tell me, you know what, it's like this too. I mean, I can give a very obvious question here. So if I give you, let's say this, let's say how about this, here we have the limit here, and then I give you this point, let's say x to the, let's say 7 power, and then minus x. And then I will give you x approaching what? X approaching infinity. Now if I give you this here, this is very obvious. What is the answer? What is the answer here? If you write infinity like this infinity is correct. Correct. Correct? But not justified. So if you write infinity like that, you know what? You get no credit on the test. Get what? Get a score. Get a score. What is your score? Your score over 0. Your score is equal to what? Is equal to 0. Okay? Don't get angry at me. So if you write that kind of statement, how many points off? 10 points off. That's it. That's it. How many points off? 100 points off. So how do you write? How should you write so that you will get the right answer? You'll get full credit. Lim, and then what? This is x to the 7th power, and then minus x. So what? So this is now equal to lim, and then this will now be x times, and then x to the 6th power, and then times what? Minus 1. And then this is the right way. So now let me just fill this in. So this equals what? 7 here. And then x is approaching infinity. And this is x 7th power. Factor of the x, and now this is x to the 6th power, and then what? Minus 1. X is heading to infinity. Okay, what is this now? This is now going to be infinity times infinity, and therefore infinity. This is now perfect work. Work perfect. You get full credit. So if you have any kind of indeterminate form, what is it that I'm looking for? I will be looking for this guy. What is that? Non-indeterminate form. This is now a non-indeterminate form. Non-indeterminate form. It's indeterminate form. That is what I will be looking for. So in any kind of limit problem, I need to see that non-indeterminate form. I need to see that. In the non-indeterminate form, there could be a result. You know, if you have a theorem, or later on, you know, when we get to chapter 2 and 3, we will be learning many of these theorems here. And so many of these theorems, or you have something, or non-indeterminate form, or let me say, or something, or what, or a form, or apply a limit theorem. Right now, you don't have that many theorems here, but if you can apply a special theorem, then that's okay too. What is the theorem? The special theorems are special rules. So they don't go by the same rule, but it's a rule. So you can bypass the common rules. So you either have to convert that into a non-indeterminate form, or you should be able to apply a theorem. It's some kind of limit theorem, and if you can apply limit theorem, then you can bypass that. But right now, we don't have that many theorems here. Okay? So either way, so I would like to see the limit of a non-indeterminate form, or apply a limit theorem at that point. A form on the theorem. But anyway, we'll talk more about that later on, okay? So I think that is it. So let me now save this and now fill this. I think we are almost done here. So let me go back here, and then now we have this property right here. Now about this direct substitution property, let's see. Should I go over this right now? You know what, let me go over this later, okay? Later, I'm going to cover this page a little bit later. And then, 0 over 0 form. You know what? Here, let me do this here. How about this? Example 9, 0 over 0 indeterminate form, but this has something interesting, so let me just spend time here. How about this? Let's do this. Example 9, 0 over 0. All of this, number 1 through number 6, they're all in a 0 over 0 form. Okay? But now let's see. What is number 1? Limit of 3x squared over x approach 0, that is 0 over 0 form. When you actually simplify this, what does this become? This actually becomes, what is the final result then? So in this case, we'll simplify what we have. x approaching 0. And then what is the argument? The argument of the limit is 3x squared over x, so this is actually 3x. So what does that become? What is the answer? It's actually 0. Well, now number 2 is also a 0 over 0 form. 0 over 0 form, 2x over x cubed. X approaches 0. So what is this equal to? Obviously, we cannot split. If you split, we get 0 over 0. So 0 over 0, we have to convert that into a non-indeterminate form. So just simplify what's in there. So 2x over x cubed. So what is it? X approaches what? X approaches what? 0. So what is that equal to? That would be 2 over x squared. So what is 2 over x squared? Can somebody tell me the answer? Can somebody tell me the answer here for number 2?
Is it infinite?
Infinity. Plus infinity? Or could be minus infinity? This is actually 0 plus minus here. But the nice thing is that in this case we have a square. Get this. So when you simplify that, we have to get 0 over 2 over what? 2 over 0 plus. And so that happens to be what? This happens to be infinity. Now number 3, this one is very easy. It's also 0 over 0, but the limit is now 3x over 2x. We can simplify that to 3 over 2. And then we have a limit x approaching 0. But note that the argument of the limit does not have an x, so this one is easy. This one is just 3 over 2. So all of these are 0 over 0 form, but we have different possible results. Now the question is the example 4 and 5 and 6, which I've never seen before. What is number 4 now?
Would it be infinity plus?
What is it?
Wouldn't it be infinity plus?
Infinity plus? Why? Number 4 we're talking about right here? Is infinity?
Would it be 0?
That would be 0. You know why? Because the 0 over 0, we talked about the 0 over 0 here, but let me tell you that 0 on top, note that this 0 right here, you know who this guy is? This guy is the scale of all. This guy is not this 0 is what I call a 0 real. It's a real 0. Whereas the bottom 0 is not a real 0. This is a fake 0. I call that the 0 form. So when you look at this example 4, note that the numerator 0 is actually a real 0. It's a real guy. It's not a fake guy. So in this case, when the real guys show up, what happens? When the real guys show up, what happens? Then you have no way to win. This guy is 0. It's not an indeterminate form. It's like this. You have x here, and we have 0 over x here. And then there's 0 here. And then what is this? If x is approaching 0. How about if we just say 0 plus to make it out the arm a little bit simple? So how about if you plug in 0.1? Let's say 0.1. Then that would be 0. How about if it's 0.001? Then that would be still 0. So what happens if you plug in 10 to the minus 1,000? The real small number now. So what is that? Then that will be still 0. See? This guy will always be 0. It's just 0. There's no competition here. So if you look at number 4, this is not an indeterminate form. Why? Because the numerator is a real 0. It's not a 0 form. It's not a fake 0. 0 form is what I call a fake 0. So this 3x and 2x here, these are all 0 form, meaning they're not real zeros. There's something heading to 0, but they're not real zeros. When the real 0 pops up, then now the story changes completely. Now let's look at number 5. What is limit of x over 0 over x over 0? What is that? Can someone tell me what this guy is now?
Based on what you said earlier, would that be undefined?
Yeah, this is not fake. This is not this one is now undefined. Undefined. Not if you say does not exist, well, not does not exist. So if you say does not exist, it's really wrong. So what is the difference between does not exist and undefined? Well, does not exist means that we have values, but the values are not approaching a single number. But if you look at this guy here, number 5, basically the picture is this. You have x here, and we have x over 0. And then now let's see what happens here. X is approaching 0 here, so these guys are approaching 0. Now for convenience, let me just approach on the positive side. Okay, so what happens if x equals 0.1? So it's 0.1 over 0, or that's undefined. Undefined. Now how about if it's 0.001?
Undefined.
It's still undefined. So what happens if you plug in 10 to the minus 1,000? Real is tiny number. It doesn't matter, because we are trying to compete against the real 0. So here, when you look at these zeros here, all the zeros we have been talking about here, these are 0 forms. But 0 form is supposed to be distinguished from a real 0. When the real 0 comes up, then the real 0 will kill everybody. There's nothing to do there. The real 0 is not the same as a 0 form. Watch out. So this guy's undefined. So when you look at this guy here, look at all these undefined, well, it's not going anywhere. This is still undefined. There's nothing going on here. It's undefined. It is not infinite, it's not minus infinite, it's undefined. So here, now does not exist means at least we have some values here. We need to have some values here, or plus or minus, and then the values are not heading to a same number, and that's what I mean by does not exist. But undefined means we don't even have any values to work with. No values here, nothing to work with. That's why when you have a limit like this, here is one of the examples I have was this. You know what? Okay, so let me cover this and clear this. What I'm going to do is I'm going to go back to one of the pages here. And one of the pages was this right here. Was, I think, was it? Let me see. What was the problem? Let me look for it. We have a few minutes here. I would like to go over to, I'm back up here. Oh yeah, this is section note 1.5a. Section note 1.5a and the example 9. The example 1a, example 9, when you look at this, example 9 is something I've not gone over, but now let's look at this. Example 9, example 9 here, this is section of 1.5a, in case you wonder where this is from. If you can see, 0715A limits, okay, that's the file name. Now, example 9, okay, so let's see what we have here. Now, what's this? This one here is what? This one here is limit, so annotate here. What is example 9 part A? Look at the limit is x is approaching 2, 0, 2 plus. This guy is actually 0 over 3, 0, 5, which is actually equal to 0. No problem. Now, what is part B? Now, note that x is approaching 2 from the minus side. That is, x is allowed to be like 1 and then 1.99, y is 1.999. Only the minus side. What is this here? This is now going to be undefined. Undefined over 5. So this is really what? Undefined. Oops. This is undefined. So let me write undefined here. This is now equal to undefined. It's not 0. It's undefined. So do you see the difference between 2 plus and 2 minus here? Where in 2 plus, you get the values are actually up for 0. But the left limits, we don't have any values here. And note that's actually complex numbers. Complex number, not allowed in this case. If we do not allow complex numbers. If we do not allow complex. Complex numbers, okay? Now, what happens if you allow complex numbers? What happens if you allow complex numbers? Then this could actually be 0, okay? But, for now, in this class, we're not going to deal with complex numbers here, so we'll just say that this one is undefined, okay? And then, now what is part C? Now, part C is not a two-side limit allow. Oops. Now, what is part C? Two-side limit, but the left side is undefined. So this one, therefore, has no choice. This one is equal to undefined also, because the left limit doesn't exist. The limit structure. Okay, you know what? I guess we'll have to do example section 1.8 next time. How about this? Example 10, let me just wrap up this one here. We've got 1 more minute to go. How about example 10 and 10 star exponential forms? Now, let's try, by the way, this algebra, we can still do it. Okay? The graph still will come in Calc 2, but the algebra is this. Now, what is this? Can you tell me? This is actually 2 to the, okay, 2 plus. So this is actually going to be 1 over 2, 1 over 0 plus. What is 2 raised to the 1 over, what is 2 to this? What is 2 to the 1 over 0 plus exponent?
1.
This is actually 2 to the what? What is this? 2 to the what power?
0.
1? Oh, 2 to the what
It's
power?
a 1, no?
What is 1 over 0 power?
0.
0.
This is infinity.
Yeah.
This is equal to what? Infinity. Do you want me to plug in a value? Let's say, how about if you plug in, let's say, x equals, let's say, 0.01. Let's see what happens. If you let x equals 0.01, then what is 2 to the 1 over x power? This is equal to what? This is 2 to what power? 2 to the 1 over 0.001. That's 2 to the 1,000. Oh. So do you see what's going on? These numbers are getting bigger and bigger. Now, what is this part B? This is going to be, what, 2 to the 1 over 0 minus. Well, what is that? 2 to the, what is 1 over 0 minus? That's minus infinity. Now, what is 2 to the minus infinity? Do you know?
Negative infinity?
No, 2 to the minus is not 0. It's equal to what? It's equal to 1 over 2 to the infinity. What is that? It's equal to, this is actually equal to 0. You know what? Since I don't have time, I'm not going to graph this, but why don't you graph y is equal to, and then 2 to the 1 over x power and see what's going on, okay? Why don't you graph this guy? Also, you can also graph y equals 2 to the x power. Graph y equals 2 to the x power. They're not the same graph. But you can see what happens when x is heading to minus infinity. That's what that is right there. What is 2 to minus infinity? This is the same thing as this. And then let this x go to minus infinity. When you actually graph this, you can figure out what's going on. Now, what is this guy here? Now, infinity here, or what is this? This is equal to 2 to the, what is that? Infinity, 1 over infinity. What is that? 1 over infinity. This is equal to 2 to what power? What is the 1 over 0? That's 0 plus. And then this is now 2 to 0, but this is actually what I call 1 plus. And then 1. All of these can be verified by your graph. When you graph these equations here, graph the functions, you'll be able to see these. Now, all of these example 10, they are covered in this course. The graphs are not covered. That's like Calc 2. But the algebra aspect of this, none of them are indeterminate forms, and therefore they are covered in this class. That's why it's here. They are covered. Again, the only thing which is not covered is the graphs are not covered. Okay, we cannot do the graphs here yet, but the algebra is covered. Okay, now it's already past time, so let me stop here. Thank you for your patience. All of you have a good day, and when you come back tomorrow, we will get to section 1.7. I'm planning to skip for now, and then we'll jump into 1.8, and then after that, we will start chapter 2. So on Friday, 1.8 plus chapter 2, get everything ready. We will begin chapter 2 tomorrow. So all of you have a good day. Thank you for your patience. Again, I will see you tomorrow. Bye, everyone.
Should we expect our next test next Wednesday also?
No, probably not next week, Wednesday. I'll try to target the next test the end of next week. So hopefully, I don't know, Thursday or Friday, well, we have to see how things go. But I'm trying to target the test either on Thursday or Friday next week.
Would you mind going over number 4 from the test?
Number 4?
Yes.
Number 4. Let me see. Okay, so let me go over let me save this, and then I'm going to clear this. Now 4, did I have an answer key to number 4 on the test? Let me see. I have one of the problems I didn't have an answer of, the graphical problem, so let me see. This is midterm 1. Did you say question 4? I see question 4, I see, okay. All right. So how about this? Here? Annotate. Okay, so I'm going to do what I'm going to do is share. I'm going to do the whiteboard here. How about, you know what, let me do this here. And so now let's look at an example here. Example, okay. So what I'll do is this. How about this? I'm not going to do the general case of example 4, but how about if you tell me what you want for W and V, and you don't have to, tell me what your ID number is, anyway, or you can just pick any number for V and W, and then I will do it for that case. How about that? So I'm going to put the limit here, and you choose the value for V and W, and I will do it for that case. So what I'm
V could be 2 and W can be 7.
Okay, so you want V to be V equals 2, and you want W equals 7? Is that what you want? Okay, so let's do that. So then now I'm going to now do that for that case. So now what is the limit here? So now what I'm going to do is the limit, yes. I'm now ready to draw the product. So we have the limit now. The limit, oops, that's a big limit. It's a limit, and then now we have the limit h is approaching 0. And then now what we have is this. And this is now going to be cube root of. And this is what? V plus 1 minus h. So V is now 2, so that will be 3 minus h. And then minus, and then our cube root of 3. And then the denominator is the square root of, what? Square root of 10 minus w, w is 7, so that will be 3. And then minus, this is what square root of, with w is 7, so that means 3 minus 2h. Okay, so is that the problem we are trying to do now?
Yes.
So this is the problem, right? Is that right? Okay, so how do you do this? Now, first of all, when it says the limit h is approaching 0, then the first thing is you always plug in. So when you plug in, well, there's no surprise here. We actually get 0 over 0 form. So that means you cannot plug it in. We have to go back. So somehow we have to manipulate this into a limit form, which is not an indeterminate form. That's the goal. Okay, so in this case, what shall we do? Well, what shall we do is now I can now copy all this now. That will take some time here. So h is approaching 0, and that h is approaching 0 here again. So you get this, and then now we have cube root of 3 minus h, and then minus cube root of 3, and then we have square root of 3, and then minus square root of 3 minus h. So now what is it that we have to multiply here? And then, of course, in this case, we will be multiplying by its square root conjugate, also the cube root conjugate. So this here, that here. So what are we going to multiply to the top and the bottom? This is what we'll do. Here now I'm going to multiply. Let me now change the color here to show that this is now this, but this is now square root of 3, and then plus square root of 3 minus 2h. So this is the conjugate of this the square root conjugate of the denominator. And so we have this. And then we have to multiply the same thing to the top. So that one, no choice. So 3 plus, and then we have square root of 3 plus 2h. 3 minus 2h. And now the numerator is also a 0 factor. When you have a factor which has a 0, which is a 0, then 0 form, then that means we also have to manipulate that. So now this is like a minus b. So how do you change that a minus b there? That's a squared. Now there's cube root conjugate. The cube root conjugate is going to look like this. The square root cube root conjugate, I know, most of you, you don't like the cube root conjugate, right? So therefore I need to put in the test, because you don't like it, right? My job as a teacher is to include everything you don't like, right? Everything the students don't like, and that will be on the test. So this is now going to be square root of, 3 minus h, and then times 3 minus h, and then times square root of 3. You can either put in one cube or separate square, it doesn't matter. Let me just write it separately here. Separately, and that will be not 3, and then plus, and then cube of 3 squared, which is 9. And then, which is this guy over here, same thing over here. You know what, let me just copy this, okay, that's okay. Yeah, this is not, so you have lots of time left, so let me just put that in here, square, and then plus 2, plus this, and then plus that. You know what, it's kind of messy, but once you get used to it, it's not so bad, but you have to get used to this. So this now times cube root of 3, and then plus cube root of Cube root of 9. So up until now, this is the hard part. And the rest of it will actually be easier. Any questions up to this point?
No.
And now the next step is, here's the next step. The limit stays there. X approaching 0. Now we are now going to multiply this guy right here. So let me now use, how about if I use, let's say, red now. So we're going to multiply this guy right here and this guy right here. Because they are conjugates. Whereas the middle guy, this guy is not. So this guy, leave it alone. When you multiply these two guys here, then a minus b times a squared plus ab plus b squared, that's a cubed minus b cubed. So what happens is we get a cubed minus b cubed, we actually end up getting minus h. That's it. That whole thing is actually minus h. And then we will, I'm going to copy the other factor, which is going to be square root of 3, and then plus, and then square root of 3 minus 2h. So now the first question is now, do you get this minus h? Or do I need to explain more? How you get that minus h?
I got that. And the bottom would be negative 4h, right?
In this case, that will be 9 minus, so that will be, if you do that, no, it's not 9. It's going to be 3 minus, and then when you multiply these two guys right here, what are we going to get here? That would be 3 minus 2h. 3 minus, so let me write. So this is going to be what? You know what? This right here, if you multiply these two, that will become this. That will be 3. Sorry, that will be what? That will be 3 minus 3 minus 2h. When you do that, then that becomes actually 2h. So that is going to be 2h in the bottom. Did you write?
Okay, I see that. Yeah, I see that.
With 2h. And then this big thing right here, and then this is so bulky. I don't know what to do with this. But anyway, you know what? How about this? I'm going to call this the green box right there. I'm not going to copy this. I'm a little bit lazy to copy all this now. So this guy actually goes up over here. So what happens is the limit is still at 0 over 0. So now what do we do? Now this h right here and this h right here, we can reduce that. So now what do we end up getting? And now, are we now ready to plug in? Yes, we are now ready to plug in. Because when you plug in here, what do you get? We get minus 1 over 2, and then minus, and then plus, and then when h is approaching 0, the square root of 3 plus square root of 3, we get 2 square root of 3. Oh, that's very nice. And then when you plug that h equals 0 into this guy right here, this green box, what we get is we get square root of 9, cube of 9 plus cube of 9 plus cube of 9. And so what we end up getting is we get 3 times cube root of 9. Oops. Let me change that to thin marker. So 3 times cube root of 9. So essentially that's it. Bring the minus sign to the front, and then this is going to be 2's are reduced. So we end up getting square root of 3 over cube of 9. Oh, wait a minute. What is square root of 3 over cube of 9? Can you simplify that? Square root of 3 over?
Isn't it just 1?
3 times cube root of 9. Now, can you simplify this further? I guess we can. All base 3's here. So this is actually equal to what? Let me see. This is 3 to the what? This is half power. And then this is equal to 3 to the 3 times 3 to the 2/3 power. I see. So this is really 3 times this. This is really this. This is equal to minus, and then what? 1 over. This is actually 3 times what? This is 3 times. This is 6 root of x. 6 root of 3. You know what? If you just give me this answer, I'll take it. Yeah, I'm not going to stick too much here. But this is, if you simplify everything, this is basically what it is. Or you can give me answer in exponential form minus 3 to the what? Minus 7 over 6. Unless you want to give me this answer. Okay, or unless you can give me this answer, and again, all of these I will accept. So you don't have to worry too much here. Negative 1 over, and then what? 6 root of what? 6 root of 3 to the 7th power. Anyway, you know what? I cannot write this at the corner. Anyway, if you give me one of these final forms, then I'll accept that. Any of them, I will accept. But you cannot. You can give me this one. You can give me that one. That's okay too. I think that's the end of this problem. Any question on this problem?
No, that answered my question. Thank you.
Okay, good. So make sure that you know the cube conjugates. It will show up. Like I said before, this semester your math teacher likes cube and cube roots and 2/3 power. These are my favorite exponents. But you might also see 4/3 power, 5/3 power, negative 5/3 power, or 7/3 power, or 2/3 power. Any of these you can go. I might give you half power or 3/2 power. I use those exponents too. But by far my favorite ones are the ones with cube roots and the threes. Cubes and cube roots. I like them. So you better know them, and they are actually quite important in this math course. So you have to fully analyze all cubes and all cube roots. You have to know all of them very well. Okay, so now let's see. Should I save this? Okay, I'll save this. Sure, why not? I'll just save this for all people to see. I hope I didn't make a mistake. Did I make a mistake here? Let me just verify whether I made a mistake here or not. Did I make a mistake? Let me see. This example 4, okay, so this is what we have, and so this is W is equal to 7, and so we get that, and then 3 times 2 over V is 2, and so we get 3 squared. I see. So yeah, it's actually correct. I just checked it. It's correct. No mistake here. Okay, so let me save it and clear. Anybody has any other questions?
Yeah, can you go over number 7 again, please?
Number 7?
Yeah.
What is number 7? Number 7. Okay, number 7. Oh, number 7. Okay, let me just do this on the whiteboard. Sure. Okay. This is actually from 7. So I'm going to just call this an example. An example is, what is f of x? So f of x is equal to what? Now this w, there's a w in here. So why don't I will let you choose the value for w. You can pick the w for your ID, or it does not be your ID. So pick your value for w, and I will do that problem for that w only. So what w do you want me to pick?
W equals 1 and V equals 2.
W equals 1 and V equals 2?
Yes,
but on this problem, there's no V, so we just need w.
Okay.
Okay, so there's no V here. So now let's see what we have here. F of x is equal to 4x. 4x, what? 4x minus w, so w is 1, so this is this, and then over, and then what is this? This is going to be x minus 4. So f of x is this right here. Now we have to compound this function 7 times, right? So now what do we do is, first, we will do this. First, find what? Find what? Find f of x. This is the first step. So how do you find the first thing? How do you do this? Now, I'm going to show this in 2 steps here. This is f of x. F of x is this right here. This is 4x minus 1, and then over x minus 4. So what is that? So now let's plug that into the function f again. So this is what you get. So what you get is this here, and then this is 4 times x here. We have to plug in here, and then what? Minus 1 over x minus 4. So this is what it is. Now instead of x, we now have to plug in this guy. 4x minus 1. 4x minus 1 over x minus 4. And then the denominator, same thing, this x. Inside the parentheses, we need to put 4x minus 1 over x minus 4. So this is actually a calculation problem, really. I just wanted to test you whether you could handle complex fractions properly. If you don't know how to handle complex fractions, that could be a recurring problem throughout this course. And this complex fraction, okay, so now what we do this. So let me put this in parentheses here, but how do you simplify it? So we're going to simplify this. This is how we want to simplify. We are going to multiply top and the bottom by 4x, not 4x here. we will multiply top and the bottom by x minus 4. And then we also want to multiply this x minus 4. Why? Because x minus 4 shows up in the denominator. So this is how we, this is the process for simplifying. Okay, so now what is that? So now here equal to, and now when you multiply that out, then what do you get? The numerator will now be this. It's going to be 4 times 4x minus 1, and then minus, and then what, 4x minus 1. That's what we get in the numerator. And then the denominator, when you multiply that by 4x minus x minus 4, we have 2 terms here. We do get 4x minus, we do get 4x minus 1 inside the parentheses, this, and then minus, and then 4 times, we do get what? We do get x minus 4. Okay, so this is the first step. The question is, do you understand this much?
Yes.
Do you get this one?
Yeah.
Yes.
Okay, then this part, then the rest of it is quite easy. There's really not much going on after this. So in this case, basically, when you multiply this guy right here by x minus 4, then we get 4 times, in the parentheses 4x minus 1, that we get that. And then minus, and then 1 times x minus 4 is x minus 4. Of course, the parentheses here. And then, you know, so now if you simplify this, this is now quite easy. 4x is 16x. This is 16x. What is this? 16x. So, okay, I'll write this down. 16x. And then what? Minus 4. And then minus 4x. And then plus 4. You get this in the numerator. And the denominator is this. The denominator to be what? The denominator is going to be denominator is going to be 4x minus 1. So let's open up that. 4x minus 1, and then what? Minus 4x. Minus 4x, and then what? Plus 16. So we get this. So when you simplify this here, what do you get? We get what is this? This is going to be 12x. Oh wait, did I make a mistake here? Yeah, I did make a mistake. Did I make a mistake? 1 second. Where did I make the mistake? I did make a mistake. This 4x minus 1 should not be 4x minus 1. It should be really what? X minus 4. Why did I write that 4x minus 1 there? This should be x minus 4. You know what? Let me erase this. Make it clean. Oops. So let me write this again. Sorry. I'll type it in. This is going to be what? This is going to be 4x minus 1. 4x minus 1. And then minus is going to be x minus 4. There we go. So when you simplify what we get in, we now get the, so I made a mistake again. I need a 4 there. When you now multiply all that, then what we get? Now we get 16x minus 4. So let me write 16x minus 4 and minus x and then plus 4. That's what we get. Yes. So when you do that now, what do we get now? What we get? Yeah, what is that we get here? We now get 15x top, and at the bottom we get 15. And now we get x. Oh, that's what it is. So let me call this number 1. Number 2. What is the original problem to this? What is the original problem to this problem? And the original problem is this. F how many times? 6 and the 7, right? I did up back to closing this right here. But anyway, you know, this one is quite easy because what is now, you know, now what, so therefore what we find is that what, therefore what is it that we found? Therefore, what we found is f of x equals x. So that makes it so much easier now. So, what is f of x? What is f of f? This 1, 2, 3, 3, we have 0. What is f of f? What is f of x? Now instead of 5, instead of 7, we can just do 5. 5, 1, 2, 3, 4, and then 5. And then what? And then X. I don't know how many points I'm putting here, but anyway, it's that, okay? And then what is that equal to? That is equal to f of f combine f of x. Yeah, the same as that. Well, with f of x equals to x. And then that is equal to now f of x. And that's it. F of x is 4x minus 1 over x minus 4. So if you write that, that's fine. If you don't write it, just write f x, that's okay. So this is the end of this problem. So the key thing was to get this f compound f of x correctly. Because you have to get x here. If you do not get this x, then of course you cannot get it. So you have to be very careful to work on this. So again, always the beginning of the problem is much more important here. So at this stage, you have no room to make a mistake here. If you did make a mistake here, then now it's irrecoverable, and you will not be able to simplify this expression here, because it is going to get so messy, and it's wrong. Okay? So this is it. Any questions here?
I don't think so.
So basically, if I we have this here, and so basically what I'm saying is this guy right here, with what we see right here, f of x, this guy right here, f of x, this becomes x. Because that's what we found right here. So that becomes x. And then you now have 5f left. So now you have 5f left. So now what is f of x? What is this guy here? That is x again. So that's x. And then after that is that. Or if you want to, you can just, see that f compound f, they all become what I call f compound f is an ident function, input x, output x. So you can kind of, cancel this guy, and then cancel this guy, and then you're left with that. Okay, but anyway, you get the answer. The answer is f of x. Or you can write it out. If you just if you just write fx here, that's okay too. That is acceptable as a final answer. With f of x is spelled out on the problem right here. So f of x.
Well, how do you end up with x and not the 4x minus 1 over x minus 4? Because if f of x minus 1 over x minus 4, right?
Yeah.
Like as you wrote.
Right. You can write it down and write 4x minus 1 and minus 1 and then minus 1 over x minus 1. If you write this, that's okay. That will be full credit as well.
That's also the answer?
Either this, or you can just leave it as f of x. Because f of x is a function which is defined on the problem. So if you f of x is right here. So if you get f of x, then that's really, that's enough. That is something I will accept. Because f of x is all written out, it's spelled out. So I will accept that.
Okay.
If you spell it completely, then 4x minus 1 over x minus 4, that's okay. And in fact,
so can I ask you afterward, at the end, can I ask you a specific question about my test?
Sure. Yeah, what is it?
Just because, I also got 4x minus 1 over x minus 4 as my answer, but I did it using a different method that I learned in high school, and so I didn't receive full credit for it, but I still got the same.
Yeah, but here's the problem. You got the right answer, but your answer is not justified. You have to clearly see where your argument breaks down in the middle. And if your argument breaks down in the middle somewhere, then obviously it's not acceptable. So you have to look at your solution and then see exactly where the argument breaks down, because that's where the argument. So in your case, I don't know how many points I gave you, but if your argument does not have a major breakdown somewhere, but in this case, there's almost really no other way. Everybody, no matter what they do, you have to have this conclusion in the middle somewhere, or something of this sort. Somebody, they got the inverse function, but here we don't have an inverse. But you have to get out somehow. If you did not get this guy here, then really your solution has a major breakdown somewhere. It does not justify. It's still correct. It may be correct, but anyway, we may be correct or may be incorrect. But the conclusion is not justified. So if you do not justify, if your solution does not justify an answer correctly in a mathematical way, then it is not acceptable. So you know what? So you can see write something true, something which is correct, but if it's not justified, you can just write the answer just like this. I mean, you have this right here, and then what happens if somebody writes, okay, so from here, and then you put the arrow here, and then you write this.
No, but I showed how I found it. Like I showed that there was a pattern between the two and how I got it for the f of like the 7 f of x's to equal to 4x minus 1, just not the same exact way as you did it, but I still like showed the way
but again, when you start guessing, that is a problem too. You're not sure whether you're here guessing is not allowed. So whether or pattern fitting is usually in this class not acceptable. Again, pattern fitting, because when it's odd is this number and the odd is that number, the argument might be correct, but again, those pattern estimation is not acceptable. Here, everything has to be precise and must fit exactly. There should be no room for guessing. So if you did any kind of guessing, then that step is not allowed. That is not. It's not really mathematics. It's not acceptable. So you cannot do pattern guessing or pattern estimation or fit in the pattern, because you don't know whether the pattern works. That is something you cannot justify mathematically. So it will be a major penalty if that's what you do. You're not proving it. You're not getting the answer with no guessing. Here, if you look at my solution, there's no guessing. Everything is exactly what it is. There's no estimation. There's no guessing. No pattern recognition. None of that. It must be exact. It must be precise and must be exact. Okay, that's the standard we need in this course. We cannot guess anymore. Okay, no more guessing. It makes sense?
I was just curious about the limit laws. Are the limit laws that we learned today all the limit laws? Like, is there a difference, like a limit law for difference?
The limit law for difference is actually the same as the limit for the sum, because it's like this. Okay, so let me erase this, clear this, and so let's say if you have a limit like this. Okay, let me write this down. So how about this example? Limit of f of x, limit of f plus g, limit of f of let me start with f of x, and then limit f of x, and then plus, and then g of x is equal to what? This is equal to the limit of f of x. Oh, sorry, f of f. Where's the capital F here? Oh, I capitalized that. F plus, and then what? Oh, wait. 1 second here. This is equal to now this, and then what? This is now equal to this minus of g of x. Minus of, sorry. I need to put a minus here. So what happens for the limit of a differential function? That can be written as minus g of x. It's the same thing. So,
okay.
Is actually the sum of the limits, because it is, again, if you have f of x minus g of x, then that is equal to f of x plus minus of x, and then you apply the limit of the sum, and which is equal to the limit of fx plus the limit of minus g of x, and the limit of minus g of x minus g of x. Because the constant can come out. So actually, there are other laws there, but there's so many laws out there, I cannot really list everything. It's like this: limit of, let's say, limit of if you have c times g of x, c times g of x is equal to what? Is equal to c times the limit of g of x, or g of x, or let's say how about the square root law? How about if you have a limit of let's say g of x like this, limit of g of x, and then this is actually equal to limit of this right here, limit of square root. Then this is actually the same as the square root of the limit of g of x. I mean, if I list all of these guys, there's no limit. I mean, I have to write 100 laws. I cannot do that.
Is there a power law too?
Yeah, sure. When you go to count 2, you have something, and you have let's say x approaching something, And let's say this is f of x raised to the g of x. F of x is the raised to g of x here. And then what is this? So can you write this as the limit of f of x? Can you write that as the limit of f of x and then limit of f and then raised to the limit of g? I mean, is that correct too? Oh yeah, this one is acceptable if result form is not indeterminate. Same rule applies here. So I mean, of course, we are not going to cover any of the exponents indeterminate form. We're not going to learn that here. But again, the same principle applies for everything. So if you have, let's say, in chapter E, we will get to this. Let's talk about if you have the limit of let's say sine of f of x. So what is this? This is the sine of f of x. Sine of f of x here. Then now we have the limit here as x approaching something. Is it equal to the sine of the limit of f of x? There are 10 million laws out there, so I cannot spell this out. And then we have the limit of f of x. Is that true too? All of these work as long as they don't cause any trouble. So all of these, we have x approaching whatever. So the question is, the result form, is that a trouble? If it causes the trouble, then we cannot get it. So let's say we have, tangent. Anyway, I can give you all examples like cosine here, and then let's say cosecant here, cosecant, and then something is heading to 0. Let's say we have 0 here, x here, and then we get this, and then what is this? Limit x approaching infinity, x approaching 0. What is cosecant 0? Well, cosecant 0 is 1 over sine 0 it's undefined. It's actually plus or minus infinity. But anyway, the result is, what? So all of these guys here, all of these laws, you can split as long as the result will not be a problem. It will not be any of those indeterminate forms.
I see. Okay. Thank you. So, that's interesting.
So I cannot. So basically, I just gave you 3 to represent the most basic forms, but all the other guys are exactly the same. Yeah.
Okay. Thank you, Professor. Have a good rest of your day.
Okay. Good. Okay. So did I answer all of your questions now, class? Sir, you're the only one now. Do you still have any questions? Hey, Summer, you did well on this test. Summer, are you there? Summer there? No, not there? Okay, then let me stop here. All of you, Summer, have a good day, and I will see you. Okay? So this is the end of the class meeting, and this is also the end of the office hour.